Hi, welcome to episode 46 of the eBPF and Cilium office hours, or eCHO, live stream. So today we are going to be talking about something that we will be previewing next week at KubeCon, or rather we're previewing today something we'll be showing next week at KubeCon. So let's quickly talk about the headlines. As always, if you're here with us today, do say hello. I see Sachin joined pretty early, so good to have you with us, Sachin. As always, we love to hear your questions, get your comments, and know where you're watching us from. So yeah, it's been a busy week in the world of eBPF. The Linux kernel developers BPF conference happened, I think it was last week. There was a lot of folks there from the Isovalent team. So we saw some pretty good pictures coming in. And in fact, on this website, you can see a picture of these folks who are building eBPF for the rest of us to build tools on top of. So grateful to all those folks. And I think they probably had some really interesting discussions last week. And speaking of interesting discussions, next week it's KubeCon in Valencia. So if you're going to be there, do say hello. Tell us, now if you're going to be there, we'll look out for you next week. So Cilium is going to be there with a Cilium project booth. And we're also going to be there in the form of Isovalent as well. There are loads of talks about Cilium, many of which are by end users. So, for example, we've got IKEA speaking at the eBPF co-located event on Monday. There's Bell Canada talking about Cilium at the Telco event also on Monday. And several other end user stories, which I think are going to be really exciting. Also, you'll be able to come and talk to us about how to get involved with the Cilium project. I want to particularly highlight this session on Thursday, where we're hoping to meet developers, technical writers, folks who want to get involved in Cilium in any form. We'd love to see you there. If you have ideas, things that you want to see implemented in the project, that's a great place to come and discuss those ideas. I can see loads of people who've joined us today. So just quickly running through to say hi to Sachin, hi to Nicola, hi to Quentin, who is moderating for us as always. Hello to Tony, Russell. We've got some regulars here. This is really great. Hello to Naveen. Hi to Kamaraju, watching us from India. So as we go into this next section, I hope you're going to find this pretty exciting new feature that we're going to be talking about. Do let us know your questions. This is going to be kind of the first time we've been speaking about this publicly, so I'm pretty excited about this. Let me welcome to the eCHO show. Let me welcome my colleague, Thomas. So thanks for joining us again, Thomas.
Hello.
Have you on the show?
Yeah, thanks. Always great to be here. I feel like I was just here, and I think I was last week or the week before.
Yeah, only a couple of weeks ago. So yeah, we'll get some different guests on next time. But I think this time it was a really great opportunity to talk about the topic of security observability. Folks who've been paying a lot of attention and who've been following us on social media and following the blog might have seen Natalia's blog about a security observability book that we've published. We'll be giving away copies of those at KubeCon next week, so do come and talk to us for one of those. Yeah, so really the topic that we're going to talk about today is Cilium Observability, and a tool that, well, we're describing it as new, but it's not so much brand new as something that has been part of Isovalent's offering for quite a while, but we're now bringing to open source as well. So Thomas, introduce us to Tetragon.
Absolutely. Let's get started. So as Liz mentioned, Tetragon, let me see if the screen share is working. I think so.
There we go.
Yes. So Tetragon is a new open source project. Tetragon provides eBPF-based security observability and runtime enforcement. And we have been shipping this to our customers as part of the Isovalent Cilium enterprise distribution. So many know us, or many know Isovalent for having created Cilium, on the CNI on networking, now service mesh. We've always been also doing runtime security, in particular around observability, and also a bit on the enforcement side. And today or next week, so this is a preview of what we will announce next week at KubeCon, we're essentially open sourcing major parts of Tetragon and making it available for contribution to the open source community. So let's look a little bit at it. So
can we just pause for a moment and acknowledge how great the Tetragon logo is?
It's amazing, isn't it? Kind of the small little bee warrior fighting with Cilium and eBPF. All right, so what is Tetragon? And I think hopefully a lot of this will make sense very, very quickly and very soon. So I think eBPF is obviously an amazing technology to introspect the system and applications. So essentially what we want to build with Tetragon is bring all the eBPF experience we have as a team. Many of our team members have been involved with eBPF since 2014 when it was created. We've created Cilium, the major CNI plugin using eBPF. We're now bringing all of that knowledge to the observability space, in particular with a heavy security focus. So if you look at kind of where eBPF can hook into, we see all of this these badges with the eBPF logo on it. These are all places in the system where we can hook in and actually gain visibility from the lowest level storage network, like disk access, network packets, namespacing, whether it's network namespaces, mount namespaces, user namespaces, the virtual file system, the network stack, and so on and so on. All of these subsystems eBPF provides visibility into, and of course also the system call layer. The system call layer, in that layer, a lot of tools already exist. I think there's a lot of system call traces that already exist based on eBPF as well that provide this visibility. What some people don't know is that eBPF can also be used to introspect the application itself. We can actually build function tracers. We can look into library usage and so on. So all
I guess we've seen some examples of that on eCHO before. So things like the flame graphs that we've seen from tools like Parker and Pixie, it could give us that indication that we can inspect the applications as well as what's happening in the kind of infrastructure layers.
Exactly, absolutely. And we're bringing that, so it's the same underlying eBPF technology that we use. And we bring that and actually look at a very security specific or quite a security centric observability focus here. So this is one level down, and we can kind of look at what are the types of observability or observability data that we can extract, right? We had talked about data access, for example, when are certain devices accessed, or looking at the network level, parsing individual protocols, whether it's HTTP, DNS, TLS, TCP. But then very interesting, actually observing the namespacing layer. This is the Linux kernel subsystem that essentially enables containers. And because it is software, it's possible that there are software bugs. And when a user or an attacker attacks the software bugs, a kernel vulnerability, escapes or breakouts can happen. And with eBPF and with Tetragon, we can actually observe them. So we can see when a container is escaping its namespace isolation. We can also see when a container is escalating its privileges. Maybe it's allowed to do so, maybe it's not. We can see both. But then we could also look into, for example, TCP sequence number attacks, or we can observe when certain file system or certain files are being accessed. For example, when somebody writes to a systemd unit file, we want to see this because it might modify the bootstrap process of the VM, or if somebody accesses etc shadow, and so on. And of course, also the system call level, and as we talked about, function calls, and so on. What's very unique and what's very specific and I think interesting with Tetragon is that a lot of the observability logic around collecting actual signal. So not just looking at the raw observability data, but a lot of this processing, for example, creating metrics or creating stack traces or creating histograms or aggregating data together, doing filtering. A lot of that additional logic is usually run in a user space agent that Tetragon has as well, but Tetragon moves a lot of that logic into the kernel of eBPF. And this allows us to perform this very deep observability with incredibly low overhead, like a fraction of what, let's say, a ptrace-based observability approach would provide. And that also allows us to actually be very flexible and use the extendability to provide, and we can zoom in a little bit, to actually provide a lot of integrations into interfaces that already exist, where we can extract our observability data too. For example, for metrics, we want to export that into Prometheus or maybe into a SIM. We want to have like a raw JSON output for events, but then also fluent integration. Same for logs. You may want to export that into a Grafana instance or into Elasticsearch. For traces, they could go into OpenTelemetry and so on. And with eBPF, we have this flexibility because we can extract the data in the form we need, and then a Tetragon agent can export them into kind of the relevant formats. So that's the entire observability piece. To summarize this, I think the deep observability, a key aspect of Tetragon. We can see everything from lower levels all the way into applications. The transparency, so no application changes are needed. It's all done from within the kernel of eBPF. So the application does not even know when it is being monitored. It's actually a difference, for example, to ptrace. If an application, if you use ptrace to trace an application, the application can detect this, that it is being ptraced. But then there's also the low overhead, because we can do so much in kernel very close to where the observability data is actually produced. And this helps us actually to gain this deep observability data, because often when you go deeper in terms of visibility, it becomes more expensive. So having a very high level of efficiency is very important. That's the observability part, which is, I think, exciting on its own. And I think this is where tooling like BCC and BPF Trace and like Pixie and others have already done quite a bit. We're, I think, bringing in a more security-centric focus here as well. So I think it's a nice complementary project to a lot of existing projects that are already out there. But then we actually bring the second aspect in as well, which is the enforcement. So besides extracting visibility data, we can also take policies, and I've listed 3 examples here: Kubernetes CRDs, or just JSON policy, and also something like, for example, a policy created by Open Policy Agent, that's this logo here, can be fed into the Tetragon agent. And the Tetragon agent then enforces these rules in kernel. So this is very, very different. And we'll look at an example in a second on how usually that's done in kind of traditional system. All of the enforcement, including all of the rule engine, is in kernel, which means we can do so-called real-time enforcement. This is the same synchronous enforcement that, for example, SC Linux or SecComp or LSM would do as well. Like as soon as you observe, as soon as the system observes behavior that is not correct, the process is immediately terminated, or the action is immediately stopped, which is very different to a system such as ptrace-based enforcement, where ptrace is used to extract visibility, and then a user space agent processes that asynchronously and then kills a process reactively. And in the meantime, until that kill signal has been sent, the process can continue and actually do more damage.
I think we've seen that kind of concept for a while. It's certainly something that I've spoken about around how, if there's a gap between the time that you detect a malicious event and actually being able to do something about it, it could be too late. Your data could have already been exfiltrated. Yep. So being able to prevent the malicious event from occurring, rather than just saying, hey, sorry, something really bad happened, but it was 200 milliseconds ago. It's a huge difference in power and the real defensiveness of that security tool.
Yeah, it can take milliseconds to extract data and send it somewhere, right? So enforcement needs to be immediate, and enforcement needs to be in real time. I think the other unique aspect of Tetragon is that it can do enforcement across multiple layers. I've listed 3, and it can do enforcement actually in a variety of kernel subsystems. We are kind of used to doing enforcement at the system call level. So this would be something like seccomp, BPF, being able to allow certain system calls to be made. And that's a great way to reduce the attack surface of the kernel. So if an application attempts to exploit vulnerability in the kernel, it can only do so if the system call that's vulnerable is actually allowed. Another example would be something like LSM or SC Linux, which has enforcement points deeper down in the kernel. And Tetragon is more like this. It can actually observe and enforce across the entire stack, not just at the system call level. You can, of course, do system call enforcement, what is allowed, what is not allowed with Tetragon, but you can do more. You can, for example, say, I want to limit access to certain files, and not at the system call level, further down, when the file system is actually being accessed. So even if the file access would happen through some other mechanism that's not a system call, we could still detect and block that as well. An even better example, I think, is the namespacing and the escape of let's say the user namespace or the file system namespace. So let's actually scroll down, let's skip a bit and look at that specific example, because I think that will make a lot of sense. Here's the picture. So a very common example, I think this is the main way how containers usually escape, is there's a Kubernetes pod running or just a container, and this container is aware of some vulnerability in the Linux kernel, and it will make a system call that then exploits the kernel vulnerability. And this vulnerability allows to execute code to escalate its privileges. So an unprivileged pod, which does not have, for example, capsys admin capabilities or is not running as root, can gain these capabilities even though it's not supposed to do so, and then break out of the container. And Tetragon can essentially observe when this scope of privilege changes in real time and immediately kill the process before it can even continue. So essentially, before the system call even returns, the process is killed. Typically, a pod here would exploit the kernel and then wait for the system call to return, and then it can do something. For example, install a rootkit or make the damage permanent, install a system unit file, or deploy a static pod onto the node. Like a variety of ways to then make the attack permanent. But for that, it needs to be able to execute further code. We do have an example down here on how that actually looks like. So let's scroll down and we'll go back. So how does this automatic mitigation of privilege and container escapes actually look like? And we're using here an example, the CV. This is a vulnerability in the net filter in the IP tables kernel subsystem that essentially allows to gain capsys admin privileges if the kernel is vulnerable to this bug. With Tetragon, we can create a policy that looks, it's a bit shortened, but it will look like this, which is essentially a Kubernetes CRD. And if you read through this, it's kind of easy to understand. It basically says, if the capabilities of the process change and capsys admin is now allowed, then execute an action and kill the process. Like send the signal kill, which will kill the process. If we install this policy into Tetragon, and then we, for example, run this CV, this exploit script is essentially the demonstration that this CV works. It will essentially set up a container namespace and then exploit the kernel bug and pop a root shell. We can see that when we run that script, usually it will actually succeed, and then you have a root shell. In this case, it just gets killed, and the root shell never happens because Tetragon observed that the capability change happened and immediately killed the process. So the kernel bug could still be exploited because it's there, or it could be, you can trigger the bug, you can try and exploit the bug, but you cannot gain a privileged escalation from it. And this is a massive benefit compared to a lot of other approaches in terms of trying to secure this, because it does not need to know the details of the CV. We could have used another CV in this example to gain the privilege escalation. It would have the same result would have happened. So that's another, I think, massive part of Tetragon that, like, besides the observability, besides relatively basic enforcement principles based on system calls, it can understand or it can enforce on a much higher level policy as well.
Got a good question here from Russell. Is this enforcement intended just for Kubernetes, or can it be for any workload on Linux?
This can be done for any workload on Linux. Essentially, Tetragon is Kubernetes aware, so it does actually understand pod data and so on, but that's why I listed here in the policy, if we go back here, the policy API, there's also just JSON, so you can actually just feed in a JSON policy that does not contain anything about Kubernetes. It could be my binary X can do these type of system calls, or if a binary matching this pattern escalates privileges, kill it. There's nothing Kubernetes specific about Tetragon itself. The agent does have Kubernetes integration, and I'm using Kubernetes as an example because I think it's one of the primary use cases that Tetragon targets. But you can, of course, use Tetragon outside of Kubernetes as well. You could use it with other container runtimes or just container runtimes, native processes, or even inside of virtual machines as well.
And I think having that Kubernetes awareness is what makes the output from Tetragon so useful. You know, you're going to see if you're in observability kind of mode, if you're not killing things, you're still going to see traces being generated that will show you exactly what process inside which pod in which namespace is responsible for the potentially suspicious event.
Yeah, we can actually look at an example here. I think we have the CLI example, which shows the Kubernetes integration. Yes, here we go. Now we'll zoom in a bit. So there is a CLI with Tetragon that can be used to essentially introspect and analyze the behavior of an application. In this case, we're actually leveraging a Kubernetes pod that is running curl-l github.com. So let's zoom in a bit. Here we go. So we see each line essentially represents an event. So we see that there's a process execution, user local bin curl -l github.com. Then we see the DNS resolution, what's happening. We see the IP that is being returned. So this is an example of Tetragon actually understanding the DNS protocol resolution, what happens on the wire there. Then we see the connect system call. We see a connect to the IP that was returned on port 80 because we did not specify HTTPS. So it's unencrypted, port 80. GitHub doesn't like that. So we see the HTTP processing. We see an HTTP request. We see this as a get to slash. But then because GitHub wants us to use SSL TLS, it returns a 301. Hey, please actually not go here. You need to talk to me on port 443, which means then curl does another DNS lookup, gets the same IP again, and now it does a connect to port 443 on GitHub. And then it gets even better. Tetragon understands the TLS handshake of the protocol. So it actually understands, okay, you're talking to github.com. That's the SNI. This is using TLS 1.3, and we have negotiated this cipher. We actually have even deeper visibility. This is just a summary. We would have all the aspects of the handshake that has been ongoing here. So we actually see, for example, if this was using TLS 1.0 something, we would see that as well. Then we see that the process actually exits. So the curl process exits with error code 0. And then we also see the TCP connections and that they have terminated. And we see the amount of data that was transmitted and received on those as well. Like as soon as a TCP connect or a close is observed, it will actually accumulate the data and understand how much was actually transferred as well. So that's an example of the CLI showing the Kubernetes integration. The Kubernetes integration is essentially this left part here. We can see that this is in the default namespace, a pod running or a pod named test-pod. If this was not running as a pod, you would simply see the process ID and the binary name here.
So this is a really great question. Do we need really modern kernels like 5.15, which I doubt very many people are running in production today, right?
Yes. So actually, that's maybe a good point to talk about kind of why we've created Tetragon, because a major reason is actually this. So let's go back, and because the short answer is no, it can actually run on much older kernels. And the reason why that's possible is because we have invested quite a bit in understanding and creating something that does not require very recent kernels. So let's go back up here. Why Tetragon? So traditionally, these were kind of ways of gaining visibility into the system. So app instrumentation, changing your app, or LD preload, or ptrace, which is an early on debugging interface that the kernel allows to trace processes, what system calls they're making. They provide some visibility, they're quite efficient, and ptrace is also transparent, but they have very limited enforcement capabilities. You can do some enforcement, for example, with LD preload, like loading a library, but an app can simply bypass that by doing static linking, and then whatever enforcement capabilities built into LD preload would not work. ptrace itself is no enforcement, so you can observe and then do asynchronous enforcement, but that leaves that race window where more damage can happen, which is why the kernel team or the Linux kernel actually imposes or creates or provides a variety of built-in mechanisms to do security. I think well-known is seccomp, I think, which is 15, 16 years or even older by now, SC Linux, and LSM. LSM is a framework, so specifically in this case would be something, for example, like LSM eBPF. seccomp is great, it's transparent, it's efficient, but it's only enforcement at the system call level, and it's very limited in what it can see. You can actually not do inspection into the system call argument, so you can actually not see what is the IP it's connecting to, or what is the file it opens, and so on, and there's no visibility, which is why SC Linux and LSM also exist. They're great, they're efficient, they are transparent to the application, but they have no Kubernetes awareness. And even worse, they're not really extendable. So LSM eBPF provides great capabilities, which Tetragon will definitely use when available to do even more enforcement, but requires a very recent 5.7 kernel. And they also, I think that's the other angle, they need to understand the actual attack vector. So they're very much focusing on, I want to only allow what is known and what is good. They're not able to understand, okay, privilege escalation has happened, that shouldn't happen, let me just kill the process, which for most security vendors left essentially the kernel module path, which is efficient, it is transparent, and it is extendable, but it has downsides as well. In many environments, you cannot load a kernel module. Loading a kernel module is a security threat on its own. Right? I think it can crash your kernel, it can compromise your kernel, and it's also very challenging to upgrade a Linux kernel module without actually turning off the functionality and then turning it on again. eBPF solves all of these problems, which is wonderful, and that's essentially why we have created Tetragon, right? So it gives us this efficiency, it gives us the transparency. The app doesn't even notice it is being observed, it's being monitored. It gives us the synchronous enforcement that LSM, that SC Linux has as well, but it's also extendable, so we can actually make the Kubernetes, or we can make the kernel Kubernetes aware, or we can build in new concepts or new protocol parsers that are needed now, and when the kernel version that somebody's using was created were kind of unknowns or not expected. And it also gives us this deep visibility into all layers of the stack. So Tetragon works even with 4.x kernels all the way back, depending on the availability of certain BPF functionality. Tetragon will use more or less, but there is no minimum kernel version that's recent. So that's a major reason why we have created Tetragon.
And I think there was a follow-up question here about how we can guarantee that this isn't going to cause the kernel to panic. And of course, that is one of the beauties of eBPF. It's the verifier that's going to keep us safe from kernel panics, right?
Exactly, right. So in this picture, we see this kernel runtime box with the eBPF logo in here. And what this kernel runtime or eBPF runtime provides is a couple of things. First of all, as Liz mentions, a verifier. The verifier will ensure that it's not allowed to load any programs that can harm the kernel. So you're not allowed to, for example, load a program that loops forever. eBPF does support loops, but they need to be bounded. So you cannot actually load a program that will then spin forever and just halt your kernel. You can also not just, unless you have very specific privileges, you can also not just access random kernel memory. You can also not just write into random kernel memory. Kernel modules can do this, and if they do, that's when they crash the kernel. eBPF programs are also subject to, for example, all the variables that an eBPF program uses, they need to be initialized. Like the verifier ensures that there is no random kernel memory state in eBPF program variables, and so on. The list goes on and on and on. There's a very sophisticated verifier in place that ensures this. The focus of this safety is very, very high, because today eBPF is used in major data centers. So a good example is, let's say, Facebook and Google. They use eBPF at the lowest levels, for example, to mitigate TCP zero days, to load balancing, DDoS protection. Security issues in the BPF runtime would be a major problem for these companies. So there's a lot of eyes on eBPF and the verifier. So I think that's essentially the main difference to a Linux kernel module and eBPF.
And I think we could see, in the BPF conference that happened last week, there's folks from Google and Meta and some of these really, high scale companies who are extremely involved in how eBPF works, precisely because they're so reliant on it and it needs to be safe for them to use.
Yeah.
So speaking of how people use a product like Tetragon, now, of course, this is something that we're open sourcing, but it's been used in production for a while. So I think we have some experience that we can use to talk about how we imagine users will leverage Tetragon. Is it just to protect tactically against particular CVEs, or are people using it more broadly to defend an entire cluster against a broad range of possible attacks?
Yeah, let's look at a couple of use cases. We have listed them down here. So let's look at them. Let's do the monitoring access to sensitive files first. This is a good start. Something that a lot of users are doing relatively early on. This is showing Tetragon integration with Splunk. This is the SIM integration that exists, and in this version, we're essentially monitoring access. In this case, it's monitoring access to etc password. Other good examples would be, I want to monitor the init scripts on my node because nobody should ever tamper with them. Or an even better example would be the Unix domain socket of the container runtime, but because whoever has access to that has essentially gained root access on the system. So I think this is the first level where across a fleet of cluster systems, whether it's with Kubernetes or without, you can gain value just from observing, monitoring access to sensitive files. Even in this case, it's actually highly useful to understand Kubernetes context, right? In this case, we not only understand the namespace and the pod name of the workload that has made the access, we can also understand the container image. So we can actually see the version of the application, for example. We see the UID and so on. This is just showing a couple of columns. We have a lot of metadata visibility that we can extract. Another example is detection of weak TLS ciphers. So for example, to enforce TLS compliance monitoring. So yes, great, your apps are using TLS. How do you know, maybe I can zoom in a little bit so we see this a bit better. How do you actually know whether your apps are using a TLS library that is using a modern version of TLS? And how do you know whether the ciphers they use are secure? How do you know whether the key lengths that are being negotiated are above 128 bits, for example? And with the TLS monitoring here, we can actually see what is being negotiated. And if any pods use insecure ciphers or weak key length or cipher key length, then we can tell. And we can tell exactly which pod, which container image version, and so on. We even see the SNI. So we even see, okay, what was the remote destination when this was used? Obviously, this can also be used to, for example, detect an SSL downgrade attack as well, when the attacker tries to intentionally kind of announce, oh, I'm only able to speak this very weak version of this cipher, and we can also detect that, for example. So these are kind of starting points. And then I think a more sophisticated version of this is that we have many users using is this combined network and runtime visibility. This is available as a Splunk app, for example, and it combines the view we had in the CLI before, like the network visibility with the system call and runtime visibility, and actually builds a tree of what an app is actually doing. And we can see, if we zoom in a bit, we see that there's a Kubernetes namespace, a pod name, and then we see the container runtime outside. We see this is a node app, and this node app was then compromised, and a reverse shell was invoked using netcat. You see the NC binary, which is reaching out to an external domain here, which the name says it's not a reverse shell, of course, right? And when we see the attacker, the attacker using curl to actually access, in this case, Elasticsearch, and then use curl again to do an HTTP put to upload something onto an S3 bucket. So this is kind of a next level. So not just monitoring, but now we're also investigating, maybe for forensic use cases, right? So you can store all of this data in a SIM, and then looking back, oh, what actually went wrong? Like this pod behaved really for some reason, or like apparently there was an attack from this time to this time. So you can really dig in and figure out what was executed, who reached out to whom, and so on. And then at the last level is this actually, that's what we have added most recently, is this enforcement capability, where we use all of this visibility for enforcement. And our goal and what we are looking to solve is to go away from having to understand every single CV, every single attack vector, and instead actually say, well, we have isolation guarantees that users want, such as the container namespace boundary, or this process is supposed to be not running privileged, then if that's violated, kill it, instead of trying to list all the potential ways to actually violate the kernel or to exploit the kernel. I think that's still also useful. In security, it's always multiple layers, but this is a great last line of defense in the end, that if the escape happens, we can terminate processes, we can kill the workload without actually understanding where the attack or how the attack even happened.
And as I feel like I often say, this cloud native approach to software architecture, we tend to put small amounts of function into each pod. We're breaking our applications across namespaces and pods. We can use that kind of these smaller pieces of function as a way to reason about what malicious behavior looks like and what normal behavior looks like. And we're already doing that with network policies, right? We're saying these services are allowed to talk to this particular other service and this external domain name, but nothing else. And we can start to make similar policies around the kind of file access that different services need, the kind of user identities, the kind of capabilities, the privileges that different workloads need. And the more we can build policies in a way that people, they don't need to dig into every single detail. Is this wrong? It becomes more a case of, if it's not right, we're going to block it. And that's exactly how that works in network policy. We should extend that to other aspects of security as well. And I think that's exactly where Tetragon is taking us.
Exactly. Yeah, and I think network policy is a very good example where we can actually combine Tetragon and network policy together, which we call runtime aware network policies. So what let's just mention is Kubernetes network policies. Like, if you oversimplify that a ton, it's essentially a policy that I can show one here that essentially says, oh, I want my front-end pods to be able to talk to my back-end pods, or it could be my front-end pods should be able to talk to CIDR 10/8 or something. But the granularity of Kubernetes network policies on the pod level, it's written here, like the network policy doesn't care whether it's curl that's invoked in the pod, or whether it's the Python script, or whether it's a node app or something else, or if it's a multiple container pod. They can all do and produce network packets or receive them. The network policy won't care. It will just allow based on pod to pod level or based on the IP level. Adding Tetragon and combining that with Cilium and to the Cilium network policy, which is the CRE that Cilium offers with richer network policy options, we can actually add runtime context. So if we scroll in here and look at this from runtime, So we can see that this policy says that this policy should apply to all pods with label name frontend. And it should then allow egress, outgoing connections, to all pods with the label name backend. But then we want to lock it down further. We want to say, yes, you can do so, but only if the binary is called app.py or pi here, in this case, a Python app. And it's only if the app is not privileged. And it's just an example. We could use other filtering language here as well. We could also parse and match on the arguments given to the, or we can match on the UID or a GID or other runtime aspects. But essentially allows us to lock it down further. Another good example would be just a container name inside of the pod. So if you have multiple containers inside a pod, just, okay, I only want my init container to do this connection, but not the actual workload. It's actually very common that users are running an init script, a bash script that may pull some secrets from Vault or do this and this and this. And this init script or this init container may need additional privileges and additional rights that the workload afterwards should not have. So if the workload gets compromised, it should not be able to access Vault just because the init script required access to Vault while it was bootstrapping. And with runtime or combining these policies, we can actually achieve that. I think this is very exciting, which means that if we take this example, if the pod gets compromised, it gains privileges, and then it, for example, extracts data from the local disk. It could not upload that data anywhere, and it could not even talk to the backend pod here because it's no longer unprivileged. So I think that's also very powerful, and it's a good example, just like if the visibility we saw before, combining runtime information and network security or network level information is incredibly powerful.
All right. If you're out there and you have questions about Tetragon and everything we've been talking about today, do type them in. Get your questions in now. We do have a question here. It's a little bit off topic, but let's go with it anyway. It's about the difference between a service proxy and a service mesh in Kubernetes. And we've been talking about service mesh quite a lot recently as well, and so I guess it's reasonable to try and talk about this question. I guess this, for anyone who hasn't been following us recently, we are Cilium Service Mesh is moving into GA, and I think that's something that will get quite a lot of attention next week at KubeCon as well as Tetragon.
Yeah. So I think Service Mesh is known, kind of, maybe if we go back to a picture here that helps to understand it a bit better. If we zoom in on the pods here, right? So we have pods running. Service Mesh is known to traditionally run so-called sidecar proxies. And the sidecar proxies are running inside of the pod, kind of where the yellow eBPF is right now. Essentially inside of the pod, they get injected, and then they run side by side in the pod, and all the traffic gets funneled through that sidecar. So it's no longer essentially app to app. It's essentially app to the sidecar of the other pod, and then other sidecar to the app. And this allows to gain visibility, and it also allows to do enforcement, but it comes at a very high cost. And it requires to run, if you run 1,000 pods, you need to run 1,000 sidecar proxies, which for some people can be worth it, but it's not a very efficient way of achieving this. So with Cilium Service Mesh, we are looking to provide the same functionality, the same service mesh functionality, such as traffic management, layer 7 observability, MTLS, so mutual authentication, retry, circuit breaking, all of that, but without using per pod sidecar proxies, and actually leveraging eBPF to do as much as possible in this layer down here, which is also transparent to the application, where we also have the same visibility and we can have the same control, but without running sidecar proxies. Then some people refer to service proxies as a proxy that runs separately in front of a service itself. So that could be, for example, an ingress controller, an ingress proxy that terminates TLS on behalf of the app. It can actually be the same proxy technology, so it could be Envoy in both cases of the sidecar and the service proxy. But the use of it, or the model on how the proxies are deployed, is very different. An ingress controller would typically run one proxy per node or a couple of proxies per node, depending on whether the proxy can do multi-protocol, but definitely not one per pod.
And I guess we're in some ways making this question a little bit more confusing to answer in Cilium Service Mesh, because the distinction between a service proxy and a service mesh, the functionality will be provided by Cilium. So it's going to be harder to draw a line and say this is service mesh and this is service proxy, because they'll be offered by the same components.
Yeah.
I think a related question here, asking about the RC, I guess this is probably asking about the GA date for Cilium. So Cilium 1.11 is the current GA available version of Cilium. We are very close to releasing 1.12. We're on, I think, the second release candidate at the moment. So just
yes, we just pushed out RC2, I think, last week. Absolutely, yes. I think there's one release block left on the service mesh side before we can push out 1.12. So we're getting very close to the final release. I mean, obviously next week is KubeCon. The team will be busy with that as well. But I think 1.12 will come shortly after KubeCon.
Another question going back to Tetragon, and this is pretty interesting question. Can Tetragon look into app data? And what if that app data was a PCI compliant app handling credit card information, for example?
Yeah. So yes, it can. Like any other privileged process on a node, it can look into arbitrary application memory. I mean, when I say yes, it can, that's with an asterisk. There are ways to not allow this. If you're interested in looking into trusted computing, there are ways for not allowing root on the nodes to look into arbitrary application memory. But if you, let's say, run a standard cloud instance, cloud provider instance, and run Linux on it, and you have privileged access, any process with privileged access and access to the kernel can read arbitrary application memory.
I think this is really going to be a question about making sure that your policies that you're installing are, well, you have trusted code. If you're loading eBPF code into your kernel, make sure it's code that you trust. Don't just, download an eBPF program from the internet and, eBPF is powerful, so use with care.
Yeah, and I think this is why it's important that we're actually using eBPF, because it provides, the capabilities there, right? So I think it must be known that I think you can access arbitrary memory, but it's the eBPF Probia that does this. And it's using a well-standardized API, and it's not random code that runs this. It's not the Tetragon agent here that will access memory of the user space application. It's via the kernel level.
Yeah. And I don't think, you need to be aware when you're putting in policies. I think one of the interesting things about Tetragon is it has an extremely flexible policy definition language. So you can hook into all kinds of places. I don't think there is a way to say read, some part of user space memory or kernel memory, but you do need to be a little bit cognizant of what you're extracting and where you're putting it. When you're logging data, you want to make sure that those logs don't contain secret information, for example. So there's all sorts of, interesting.
I think that's actually it's actually a great reason why Tetragon needs to exist, because yes, Tetragon has the privileges to do this, but Kubelet as well. Like Kubelet runs as root and can access arbitrary application memory data in the end. So I think it's very, very important that you have the observability and you can restrict because not every process is required or really needs to access arbitrary user space memory, but many of them have the privileges, and it's coming back from, I think, a traditional Unix, Linux security model where it was root and others, and the fine-grained capabilities that were introduced later, we're still in the process of really rolling them out. A lot of processes still run as root and have very, very wide-reaching capabilities and privileges. So it's really important to have something like Tetragon to understand what's going on and restrict it as well.
So we've got a great question here about why it's called Tetragon, and I actually have a picture that I want to show to explain this one. This is actually from my talk that I'm going to be giving at SecurityCon next week. So Tetragon or Tetragonisca is actually a category of bees. And so there are these Tetragonisca bees that are, and I love the description of this particular one because I think it's very apt. It's a very small bee and it builds unobtrusive nests. It produces large amounts of honey and it's not a threat to humans. I feel like that's a very good kind of parallel for what Tetragon is. It's very small probes. It's using very small amount of resources. It's very efficient, and yet it's going to produce a large amount of very sweet information. So that's why it's called Tetragon. Okay. Here's another good question. Are there going to be any use cases for the rule engines? And of course, the answer is going to be yes.
Absolutely, yes. And I think once we publish the GitHub repo next week, there will be examples of policies that you can use for observability, for enforcement, and so on. And then if you want to have like a predefined rule set that is available in one of our products as well, where the entire mitigation is a bit more automated and you don't have to load the rules manually. But there will be plenty of examples in the open source repository and how you can leverage and use Tetragon for both visibility and enforcement as well.
And I will be showing at least one or two cases in my talk on Tuesday. So if you're there at SecurityCon, the co-located event at KubeCon, do come and watch that. The videos will be available shortly afterwards. I'm sure we'll be showing it in a future episode of eCHO as well. So yeah, there will be examples. There's also going to be an online tutorial that we're putting together so that people can try it out for themselves. All right. So I mean, there's a lot of people saying some really nice, positive things about Tetragon, which is wonderful. So thank you very much, everyone, for your positive comments. And I think that's pretty much everything we wanted to cover today, right? And unless you have any last words you want to add, Thomas?
I would say we're super excited that we can now also engage. We've been engaging with customers on this for a long time, several years, and we're super excited that we can now collaborate with the entire open source community. So help us take this to the next level. I'm sure we see so much potential with Tetragon, and we feel like now is the perfect time to let as many people as possible to try it out, to contribute, and to build stuff with Tetragon, right? I think that will be a very exciting phase that's now coming.
Absolutely. So my thanks to Thomas for spending time with us again today. And thanks to everyone who's been watching and sending us in your excellent questions. Thank you for that. As I say, if you're in Spain next week, do come and say hello. We would love to meet you in person. And if you're not there, we'll catch up with you online very soon. Take care, everyone, and we'll see you on eCHO again soon.
Bye, everybody.